All right, Chemistry 11, 10 students. We're going to start in here with the second portion of Chapter 4, and this is all about periodic trends that we see. So first off, we're going to talk about the effective nuclear charge, and that's actually the positive charge that any electron sees in an atom. So if you have an atom or an element with multiple electrons, they are simultaneously attracted to the nucleus and repelled by one another. The result is that there is shielding. So electrons that are closer to the nucleus sort of cover up part of the positive charge in the nucleus, and the outer electrons don't see it. And so core electrons, which are the electrons in a closed shell, are very effective at shielding. And so as a result, this effective charge increases steadily from the right to the left in a periodic row because those core electrons remain the same, but the Z number, the number of protons, increases. And here we have an example across the second row of the periodic table. In general, that effective charge is equal to the number of protons minus a shielding constant, which is something that has to be looked up. It's not something you would know or could figure out. So while the effective charge increases going from left to right across a period, it changes very little going down a column, because as you go down, you have that shielding from, you have more protons, but you have shielding from those closed shells of electrons. So this has an effect on atomic radius. Atomic radius will increase as you go down the periodic table, because at each electron, as you change rows, you're going to a new quantum number, and so they are further from the nucleus. The atomic radius will decrease as you go from left to right because of that increasing effective charge. And here's a really nice diagram that shows you what this looks like. It makes it easier to remember. And so here's a question where you might be asked, with just looking at a periodic table, to think about the order of increasing atomic radius for phosphorus, sulfur, and oxygen. And so what you want to remember is going left to right, they're getting smaller, and top to bottom, they get bigger. Oxygen is above both sulfur and phosphorus, so it's the smallest. Sulfur is just below oxygen, so it's bigger than oxygen, but phosphorus is to the left of it, so it's bigger than sulfur. So ionization energy is the minimum energy required to pull that electron off, and the result is an ion. That's a species that has a net charge. Here's an example of a reaction pulling the electron off of sodium. Sodium has an ionization of around 496 kilojoules per mole. That is the first ionization energy. That's pulling off the most loosely held electron. And here's some ionization energies tabulated for the representative elements. And you can see that sodium was 496. Lithium, which is smaller, those electrons are closer to the nucleus, takes more energy to pull an outer electron off of it, whereas potassium, that outer electron is further away than in sodium, so it takes less energy to pull it off. So as that effective charge increases, ionization energy increases. So it increases from left to right across a periodic table. Electrons are held more tightly as you go across. And so you can actually chart the ionization energy versus the atomic number. And this gives you a really nice picture of the periodicity of this particular property, and we see this kind of periodicity repeated over and over with the periodic table arranged the way it is. So there's a couple of other things we can think about with ionization energy. And that is within a given shell, so principal quantum number 3 or principal quantum number 4, electrons that have a higher value of L are higher in energy, and therefore they're easier to remove. So an electron in a p orbital is easier to remove than one in an s orbital. And here's a little diagram of that. And so if we look at lithium, the next element is beryllium. So we've filled our s's there. And then when you go to boron, you get a drop in your first ionization energy because you're putting one electron up into that p orbital. It's also easier to remove a paired electron because that electron is actually getting pushed out. It's feeling a repulsion from the other electron in the same orbital. And so a good example of this is nitrogen versus oxygen. And so oxygen is the third from neon, and you can see that its ionization energy is actually lower than nitrogen's because oxygen has that electronic diagram on the right where you're putting one paired electron up in the p orbital. Okay, so it turns out you can actually remove more than one electron. There's further ionization that's possible, and it's going to take a lot more energy to remove additional electrons because it's harder to pull an electron off a cation than it is an atom, because those electrons of a cation are experiencing a true positive charge. And the other thing is it's harder to pull off a core electron, which is in a nice closed shell. Core electrons are closer to the nucleus, and they have a greater effective nuclear charge because of there's fewer filled shells sort of covering up that charge from the nucleus, fewer filled shells than there were for valence electrons. And so you can see this pretty readily here. We can take any one of these. Let's take carbon. It's got 4 valence electrons. So you can take off those first 4. The first one takes you 1,000 kilojoules per mole, but the fourth one takes you 6,000. It's not that bad, but when you have to get into the core electrons, then it's up to over 37,000 kilojoules. So it's really hard to open up that set of core electrons. So here's a question: would you expect sodium or magnesium to have a greater first ionization energy, and which would have a greater second ionization energy? So if you look at this, sodium has 1 valence electron, magnesium has 2, just looking at them in the periodic table. So the first ionization for magnesium is going to be greater than for sodium because magnesium is to the right on the periodic table, and so it has a greater effective charge and it's more difficult to remove. But if you go to the second ionization energy, it's going to be much higher for sodium than for magnesium, because for magnesium you're just pulling off the second valence electron, whereas for sodium you have to remove a core electron, and that's very difficult to do. Another thing we want to look at is electron affinity, and that's the energy when you add an electron. And so in this book, electron affinity is the energy that is released when an atom accepts an extra electron. So if we look at chlorine, chlorine loves to take an electron, and so you get a neutral atom becoming an anion. And we can see there is some trends here as well. Chlorine is 349 kilojoules per mole, whereas fluorine, it is slightly lower. It's a smaller atom, and those electrons you want to add are closer to the nucleus with the positive charge, so they're more readily accepted. Electron affinity increases from left to right. It's easier to add electrons as the positive charge of the nucleus increases, and so we get another chart with some periodicity. You'll notice that the ones at the very top with the highest electron affinity are all halogens. The periodic trend here is a little bit different. So it's easier to add an electron to an s orbital than to add one to a p orbital, once again because that p orbital has higher energy. And so this is just the same example or kind of diagram we looked at before. Within a p subshell, it's easier to add an electron to an empty orbital than to add it to one that already has an electron, because you have to pair them up and you have to overcome that repulsion. You can add more than one electron to an atom. It's done frequently with oxygen. So the first one may be positive, but the second one is always negative because it's very hard to put that second electron on. So instead of being positive, it becomes negative. You have to overcome the repulsive forces. And so the question here is, for each pair of elements, indicate which one you would expect to have a greater electron affinity, first electron affinity. And so what you look at is the effective nuclear charge. So if you look at silicon and aluminum, aluminum is to the left of silicon, and so silicon has a higher effective charge, and therefore it's going to attract an electron more readily. Whereas silicon and phosphorus, you have the same kind of idea. But in top, there is a greater affinity, but you have the fact that it's a partially occupied 3p orbital, and you've got to overcome the repulsive force of that electron that's already there. And here's just a diagram to help you better see that answer. All right, that's it for this section.